Ever wondered how engineers predict when a machine might fail before it actually does? It's like having a crystal ball for complex systems, something that could save billions in downtime and prevent disasters. Let's dive into the science behind this fascinating field, predictive maintenance and prognostics. At the heart of this work is a big challenge. How do we accurately forecast the remaining useful life of machinery? Think of it like guessing how much longer your car's engine will run before it breaks down. Traditional methods relied on fixed schedules or simple sensors, but modern systems need smarter solutions. One breakthrough comes from multi-objective optimization algorithms, like the NSGA-II non-dominated sorting genetic algorithm II, introduced in 2002. Imagine a team of engineers racing to design the best possible solution, but instead of one goal, they're juggling multiple priorities: cost, reliability, and performance. NSGA-II helps find the Pareto optimal solutions, those that can't be improved in one area without sacrificing another. This is crucial when balancing trade-offs in complex systems. Think of it like planning a road trip. You want the fastest route, but you also need to stay within budget and avoid toll roads. NSGA-II is like a GPS that shows you all the best routes, letting you choose based on your priorities. In engineering, this means finding filter settings for SFRFs that balance accuracy, simplicity, and reliability, without overcomplicating things. In this study, researchers used NSGA-II to fine-tune SFRFs, which act like biological filters inspired by the human eye. These filters highlight subtle changes in vibration signals, much like how our retinas detect edges. By testing thousands of configurations, the algorithm found the sweet spot where predictions are both precise and easy to interpret. Here's the kicker: the optimal SFRF settings didn't always follow traditional assumptions. For example, the surround part of the filter, meant to suppress noise, didn't need to cover a wide frequency range. Sometimes a tighter focus worked better. This shows how evolution-inspired methods can uncover counterintuitive solutions. The result: a system that doesn't just predict failures but understands them. By blending biology, evolution, and smart algorithms, engineers are creating tools that keep machines running longer, safer, and smarter. And that's not just science, it's a game-changer for industries worldwide. So next time you see a machine working smoothly, remember, it might be powered by a little bit of biology, a dash of AI, and a whole lot of clever engineering. Thanks for watching, stay curious, and we'll see you next time. But here's the deeper question: how do we translate these theoretical breakthroughs into real-world reliability? The answer lies in degradation modeling, a framework that tracks how systems wear out over time. Think of it as a detective game. Instead of waiting for a breakdown, we're trying to spot the clues before disaster strikes. Traditional methods like the MIL HDBK-II 17F handbook rely on historical data to estimate failure rates, but they're like predicting a storm based on yesterday's weather. That's where physics of failure models come in. These systems analyze acoustic emissions, vibration patterns, and thermal signatures to detect early signs of wear, like listening for the faint creaks of a bearing or the shaky rhythm of a motor. Recent breakthroughs are using machine learning to supercharge this process. Imagine a neural network trained to recognize the unique voice of a motor, how it sounds when it's healthy versus when it's about to fail. Or algorithms using multifractal analysis to detect microscopic cracks no human could see. Some systems even employ self-attention autoencoders to create custom health indicators, teaching computers to understand when something is off. It's not just guessing anymore, it's pattern recognition on steroids. But here's the catch: no model is perfect. That's why scientists are now building in uncertainty quantification. Think of it like a GPS that doesn't just show you the route but also warns, hey, there might be a traffic jam ahead, better leave extra time. By combining real-time sensor data with smart recursive models, they're making predictions more reliable. It's the difference between a guess and a well-informed hunch. So what's the big picture? Degradation modeling isn't just about fixing problems, it's about preventing them. From airplanes to smartphones, these tools are keeping our tech safer, smarter, and longer lasting. And as machine learning gets better, the future looks like a world where machines don't just work, they predict their own futures. What do you think? Ready to hear more about how AI is changing the game? Let me know in the comments, because the next chapter is even wilder.